Hello everyone, and welcome back to the good stuff that we have been doing. Today in this video we're going to try to solve this beautiful integral right here. So it says this is integral from 0 to pi of tan inverse of 1 plus cosine x dx, and it says this equal pi times cotangent of square root of phi. Here we understand this phi to denote 1 plus square root of 5 over 2, which is the golden ratio. Then you would have 1 over phi here to be square root of 5 minus 1 divided by 2. Alright, so this is more like the conjugate of the golden ratio. But you see how beautiful this integral is. It's quite connected to the golden ratio and even features a pi. But then it is quite intimidating because of the 1 plus cosine x, but this can be taken care of because first off, we recognize the argument as the formula for cosine, which says that cosine squared x, cosine squared of 2x is 1 plus cosine of x all divided by 2. So if we apply it to this integral, I here would equal the integral from 0 to pi of the tan inverse of what? Instead of then you have a 2 cosine squared x over 2, then you would have dx. Now let's scale it a bit. Let's scale the argument. Let's take x as x over 2. So basically dx here, 2 dx would be scaled to dx. Okay, then and also when x is pi, we get pi over 2. So this is going to be twice the integral for 0 to pi over 2 times the tan inverse of 2 cosine square x dx. Now we're going to use this beautiful formula, and which is that the integral from 0 to a of x over 1 plus x squared t squared is tan inverse of ax, of course dt. So tan inverse of ax is the integral from 0 to a of x over 1 plus x squared t squared dt. Now this, I have used it in many of my solutions, like almost all my solutions I use this formula. So please I've already explained why I use it in many videos, so I'm not going to do it in every video, but do check all my old videos. I'm going to see the reasons why I use this formula because it always works. So basically now we're going to have to write this to be twice the integral from 0 to pi over 2 of tan inverse. And then, no, we're not going to write the tan inverse now because it will be replaced by the double integral. So you would have the integral from 0 to 2 here, a equals 2. Then you have a cosine squared x divided by 1 plus t squared. Then you would have a cosine to the 4th power of x dt. Then at the back you have dx as usual. So now we have transformed this into a double integral. We could write this as twice the integral from 0 to pi over 2 times the integral from 0 to 2 of, then this cosine squared x, let's write it as cosine squared x, but then at the bottom part, because cosine to the 4th power is difficult to deal with, because you might feel like, okay, let's just do Weierstrass substitution. Let's just take t to be just tan of x over 2. No, let's just take t to be tan of x over 2 or something. Then cosine x probably will be 1 minus t squared divided by 1 plus t squared all to the 2nd power. But we're going to be dealing with 4th power expressions. So instead, let's factor it using Euler's complex number formula. So you have a 1 minus I t squared. Sorry, not even t squared. You have a 1 minus it cosine squared x. Then you have a 1 plus it. Then you have a cosine squared x also. Then you would have a dt dx. Okay, now this is just, we just factored it out. Then if you use partial fractions, I already have done partial fractions for this, but you can just take a to be cosine squared x. Then I did partial fraction for a over 1 minus ita, and then divided by 1 plus ITE. So if you do that, you would have this 0 to pi over 2 times 0 to integral from 0 to 2 of, you have a, first of all, you factor out 2IT. Then in here you will have a 1 over 1 minus IT cosine squared x, and then minus 1 over 1 plus IT cosine squared x. Then you have dt dx. Next, we're going to switch the order of integration, and then we're going to first integrate with respect to x. So that will leave us with, this is twice the integral. So the 2 cancel out even. No need to write 2d, because the 2 already will cancel out each other. Then next, you will have just say 1 over I times the integral from 0 to 2 of, then you would have 1 over t here. Then you would have, for the inside expression, you have to integrate integral from 0 to pi over 2 of dx all divided by 1 minus I cosine squared x. And then the same thing, the integral from 0 to pi over 2 of 1 over 1 plus IT cosine squared x dx, and everything is at the outside. You have a dt, so 1 over t is taken out of the expression. Now this is the time where we can use Weierstrass substitution, because already here we have just a cosine squared. Okay, if we take t to be tan of x, or we take u, let's say we take u to be tan of x, then how do you express cosine squared in terms of tan squared? Well, understand that cosine squared, you could write this as cosine squared x is 1 over secant squared x, which is just 1 over 1 plus tan squared x. Okay, so which is going to be 1 over 1 plus u squared. All right, now what about du? Well, du divided by 1 plus u squared will be dx. Okay, so, and what about the limit of integration? When x is 0, u is actually 0, but when x is pi over 2, u would be infinity. So you would have a 1 over I times the integral from 0 to 2 of 1 over t, and then you would have a integral from 0 to infinity. Then you have a 1 over 1. Let me write this below so I will have ample space to, okay, I need to have enough space to illustrate what I'm going to illustrate here. So you would have a 1 over I, okay, then you multiply this by integral from 0 to 2 of 1 over t, and then you have integral from 0 to infinity of 1 divided by 1 minus I. Okay, there's a t here actually. 1 minus it all divided by 1 plus u squared. Then you have a du all divided by 1 plus u squared. Same thing happens here, integral from 0 to infinity of 1 over 1 plus I. Yes, it over 1 plus u squared, and then you have du over 1 plus u squared, and then dt, which is going to be 1 over I over here. Then you would have the integral from 0 to 2 of 1 over t. The 1 plus u squared cancel out, so you have integral from 0 to infinity of 1 over, you have a 1 plus u squared minus it du minus the integral from 0 to infinity of 1 over 1 plus u squared plus it du, then dt. So right here you can see that a lot of progress is being made here, but I know you are wondering what about the I outside and the I inside? Well, everything will cancel out neatly at the end. When you do the right things, everything will turn out good. So let's do the right thing first. Then you would have this to equal 1 over I times the integral from 0 to 2 of 1 over t. Then you write this as the integral from 0 to infinity of square root. So you have a square root of 1 plus u squared. No, not 1 plus u squared rather. You would have a square root. Let me put it in black. So you have a square root of 1 minus it. So you have square root of 1 minus it all squared, then plus u squared, then du. Then on this other side, same thing, 0 to infinity. So you have a 1 over square root of 1 plus it all squared plus u squared. Notice that because this is a complex square root, we don't have to worry if maybe it is less than 1 or bigger than 1, because complex numbers, you don't have to worry about magnitude when it comes to complex numbers, because such things don't exist. Okay, then you have dt. Next up, you would have, this is integral from already this integral is same thing as arctan. So you have 1 over I times the integral from 0 to 2. On one part, you have a 1 over square root of 1 minus it times the tan inverse of u, all divided by square root of 1 minus it. Then from 0 to infinity minus 1 over square root of 1 plus it times the tan inverse of u divided by square root of 1 plus it. Okay, from 0 to infinity, and then you have the dt. So if you evaluate the tan inverse of infinity is basically pi over 2. So you have a 1 over I times the integral from 0 to 2 of, on this part you will have a pi over 2 times 1 over square root times t, because of the, okay, there's a t outside here, times t times square root of 1 minus it minus pi over 2 times t times square root of 1 plus it dt. So we're making some progress here. Let me shift this over to this side. Okay. Yeah. Now this will be equal to, you can factor out the pi over 2. So pi over 2I times the integral from 0 to 2 of, you have, notice that if you try to do these integrals individually, it will actually diverge. So we have to combine the integrals. So you have a 1 divided by square root of 1 minus it minus 1 divided by square root, so t rather, t divided by square root of 1 plus it dt. Now this is where you would call the deadlock, because it's difficult to proceed from here. What do we do? Well, if you recognize the fact that you have a 1 over t and you have an it, you need to think about in terms of cosine of x minus I sine of x. So if you take out cosine of x, you have cosine of x 1 minus I tan of x. So if you look at this expression now, look at this, if you say, okay, why not set t to be maybe tan of x? Maybe good thing may happen. It may be easy to simplify this, and also recognize that cosine of x plus I sine of x actually equal e to the ix. So something can happen, of course. So it's not, all hope is not lost yet, because even though things started off nicely when we recognize, let's go back to the beginning of the work. So at this very stage where everything began, when we recognize this formula, so things turned out nicely. It looks like we're making some progress. Then all of a sudden it looks like, oh, nothing is really happening again. Well, that is how life is. Sometimes it looks like nothing is happening, but something is actually happening. Now, for here now, let's stick with our initial plan and take t to be tan of x. If we take t to be tan of x, what happens in this aspect? Then dt, this is dt, then dt would be secant squared x dx. Then the limit of integration, it would be this is pi over 2i. So you have the integral from 0 to tan inverse of 2. Okay, so you have a let's first talk about t. That is 1 over tan theta. At the bottom you have a square root of 1 minus I tan theta, and then you have minus 1 over square root of 1 plus I tan theta. So let's okay, and you have secant squared theta d theta. So we're sticking to our original plan. Then here this would become pi over 2i times the integral from 0 to tan inverse of 2. Then you would have a cosine theta, right, divided by sine of theta times 1 over cosine square theta. This will be multiplied to 1 over square root of 1 minus sine 1 over I sine theta all divided by cosine theta. Then you subtract this from 1 over the square root of 1 plus I sine of theta all divided by cosine of theta d theta. So this is the part whereby it looks like we are making progress, then we hit a dead end. Now it looks like maybe something may be happening. Hopefully we pray that everything simplifies out nicely. So this is pi over 2i. You have the integral from 0 to tan inverse of 2. Now the cosine cancel out. You have a 1 over sine theta cosine theta times here. If you do the simplification, you have at the very top cosine square root of cosine theta. At the very bottom, you have a square root of cosine theta minus I sine theta. Here you subtract this from square root of cosine theta, and you have at the bottom square root of cosine theta plus I sine theta, and you have the theta. So now at least we have something to pull out of the numerator. Let's drag it out. So you have this is pi over 2i. We're going to drag out square root of cosine. So you have 0 to tan inverse of 2 of square root of cosine theta all divided by sine theta cosine theta. Then you would have here at the very top, at the very bottom here, this will be 1 over e to the negative I theta over 2 minus 1 over e to the I theta over 2, because I already explained here that cosine of x plus I sine of x would equals to e to the I ix, and then when you take the square root, it will equal e to the ix over 2. So we don't need to worry about that. So you would have pi over 2i times integral from 0 to tan inverse of 2. You have square root of cosine x divided by sine, no, not x, theta, sine theta cosine theta. Here you actually have e to the I theta over 2 minus e to the negative I theta over 2, because you know that 1 over x is x to the negative 1 power. So the theta. Now we are going to recall the definition of cosine in terms of Euler's formula. We say that we define the sine and cosines to be sine of x is equals to e to the ix minus e to the negative ix all divided by 2i, while cosine of x is defined to be e to the ix plus e to the negative ix all divided by 2i, right? Yeah. Maybe I don't even think cosine has I to it though, but the formula that is important for us is the sine now. So this is going to be equals to pi over 2i times the integral from 0 to tan inverse of 2. Then you have a square root of cosine of x all divided by sine. Why do I keep writing x? All divided by sine theta cosine theta. Then you have here 2i sine of theta over 2. Of course, now the 2i cancel out finally. Then you would have the integral from 0 to tan inverse of 2. Then you have square root of cosine theta sine of theta over 2, all divided by, now for this sine theta we can write it as twice, okay, don't forget the pi, twice of sine theta over 2 cosine of theta over 2. You have cosine of theta and you have the theta, of course, don't forget the theta. So then here you would have pi times the integral from 0 to tan, pi over 2 rather, to tan inverse of 2. Then you would have 1 over cosine of theta over 2, and then you have square root of cosine theta when you simplify, so the theta. So now you can see that what took us here was this integral, from 0 to pi of tan inverse of what, 1 plus cosine theta d theta. And this simple integral took us to this integral now. Now it remains to compute this integral. Now this is not, at the first time, this is like the second roadblock we're meeting, but the first roadblock was really scary because it contained complex number and square root, and it's not so easy to handle. But we have tried our best. To get to be able to handle it. Let's get to it. This was the first roadblock we met, but we tried. We did good substitution, and then we came, and then we have something nice with us here. Now it remains to compute this integral. Okay, of course, obviously, you know that the first thing is to get rid of this square root. So let's see, approach it. So let's get this to be equal to pi over 2. Then you have the integral from 0 to tan inverse of 2. Then you have a 1 over, no, instead of 1, at the first stop, you have a cosine of theta over 2. And then you have a cosine squared of theta over 2. This will be square root of, now recall the addition formula, this double angle formula. This will be square root of 1 minus 2 sine squared theta over 2 d theta. So you could write this as pi over 2 times the integral from 0 to tan inverse of 2. Then you have cosine of theta over 2 times the integral times 1 minus sine squared of theta over 2 times square root of 1 minus 2 sine square of theta over 2 d theta. Of course, substitution now is obvious. You have to take t to be sine of theta over 2. The only problem now is this angle. How do we find the corresponding value of t for theta? Well, we just have to go back to trigonometry. You see all those things we learn in elementary trigonometry whereby you are learning how to simplify inverse angle. Well, it's coming back to haunt us here. Oh boy. So to do that, set t to be sine of theta over 2. Then if theta is tan inverse of 2, you will have t to be sine of half of tan inverse of 2. Now this is like, now if you take u to be half of tan inverse of 2, that means we're looking for sine u. We're looking for sine of u to be t. So let's compute sine of u. Well, if u is half of tan inverse of 2, then 2u would be tan inverse. 2u would be tan inverse of 2, which means that tan 2u, 2 would equal to tan of 2u. And if we assume that we have a, let's draw it here. If we assume that we have a right triangle this way, where here is the 2u, and this is 2, this will be 1, then this will be square root of 5. Then basically, tan of 2u is known, but let's say cosine of 2u would be 1 divided by square root of 5. And we know that cosine of 2u is 1 minus 2 sine square u is equal to 1 over square root of 5. So now we can find sine u with this equation. Because from over here, you could write this as, let's see, you could write this as, okay, 2 sine square u is equals to 1 minus 1 over square root of 5, or this is square root of 5 minus 1 over square root of 5. So basically sine square u is half of square root of 5 minus 1 over square root of 5, which is, we already know that 1 over phi is defined to be square root of 5 minus 1 divided by 2. So basically this is 1 over phi square root of 5. So basically sine of u that we're looking for is the square root of 1 over phi square root of 5. So 1 over phi square root of 5. So now we come back to our integral where it is equal to, the integral we had was the integral from, let's see, it was pi over 2 times here. Okay. What we had was from 0 to pi over 2. No, we still need some things at the top here. From 0 to pi over 2. No, not pi over 2. What am I even saying? Okay. So this was, what we had is just pi over 2. Well, yeah, times the integral from 0 to tan inverse of 2. So you had the not even a half. So you had a just cosine of theta over 2 d theta, all divided by 1 minus sine squared theta over 2 times square root of 1 minus 2 sine squared theta over 2 d theta. Now like I did mention, we're going to take, say, t to be sine of theta over 2. Notice here that dt would be 1 over 2 cosine of theta over 2 d theta, which is already handled out. Then this will be pi times the integral from 0 to square root of 1 over phi square root of 5 times dt, all divided by 1 minus t squared times the square root of 1 minus 2t squared d. Okay, we already have the t. Now, of course, we are still going to take square root of 2t to equal to sine theta. Crazy substitution, but we have to do it. And this one, let's see, that means dt would be 1 over square root of 2 times cosine theta d theta, right? Yeah. Then what about the limits? Well, t would be theta would have to be sine inverse of square root of 2t, whereby if t is that, so it will have to be sine inverse. If t is at the square root of 1 over phi root 5, it will be sine inverse of 2 all divided by phi root 5. So that is all. So we would have, okay, we would have pi times the integral from 0 to sine inverse of square root of 2 divided by phi root 5. Then you would have dt over here. What is dt? We have mentioned dt to be 1 over square root of 2 times the cosine of theta d theta. Then at the bottom right here, you have a 1 minus sine. This is 1 minus half of sine square theta here, sine square theta. Then you would have a square root of 1 minus sine square theta. So we have tried our best. The main thing is to get rid of that square root term. So then this would be pi over square root 2. Then you would have the integral from 0 to sine inverse of 2 divided by phi square root of 5. Then you have this cosine, this 1 minus this square root of, let me just write it down, no need. This is cosine theta all divided by, okay, 1 minus half of sine squared theta times cosine theta d theta. So they cancel out. This is what I wanted to say. Then at the very top, you will have a 2 pi over square root of 2 times the integral from 0 to sine inverse of 2 of square root, sine inverse of square root of 2 phi square root of 5. Then you would have a d theta all divided by 2 minus sine square theta. And of course, first of all, we are going to transform the numerator into cos. So this will be pi divided by square root of 2, I believe. Because 2 over square root of 2 is basically 1 over square root of 2. So it's pi over square root of 2. Then you have the integral from 0 to sine inverse of square root of 2 phi square root of 5. Then 1 minus cosine squared is 1 minus cosine squared. That would be the theta all divided by 1 plus cosine squared theta. Now we can divide top and bottom by cosine squared theta. So you would have pi over square root 2 times the integral from 0 to sine inverse of 2 over phi root 5. Then you have secant squared theta d theta all divided by secant squared theta plus 1. Okay, yeah, secant squared theta plus 1. Then, okay, I was thinking in my brain that probably 1 plus secant squared theta is tan squared theta, but no, actually it is actually 1 plus tan squared theta that is equal to secant squared theta. So the bottom would be pi over square root of 2 times the integral from 0 to sine inverse of 2 over square root of phi root 5. Then you have secant squared theta d theta, and you have 2 plus tan squared theta. Now if you take u to be tan theta, this is where we're going to do another substitution now. Sorry about the substitution. So here we're going to take u to be tan theta. Of course, the u would be secant squared theta d theta. But the problem now is the argument. Well, theta would basically be tan inverse of u. Now, so we need to just find. Let's say if theta becomes sine inverse of square root of 2 over phi root 5, that means we need to find u, which is the tan of what? The tan of sine inverse of square root of 2 over phi root 5. Now, how do we handle this? Well, to handle this, we need to first of all take u to be sine inverse of square root of 2 phi root 5, which means that sine u. So that means we need to find tan of u. But that means sine u, the sine of u would be square root of 2 over phi root 5, okay? Whereby you would have an angle with here as 1 and here being square root of 2 over phi root 5 and here being x. So if you solve for your x, you are going to get tan u. The angle would become square root of 2 over phi. So this whole integral we call, let me check it out, we call pi square root of 2 times the integral from 0 to 2 over square root of phi times du over 2 plus u squared. So you see how everything has simplified out, and this is going to give you pi times cotangent of phi of square root of phi when you compute the integral. So because everything here is pi square root of 2 divided by square root of 2 times the tan inverse of u over square root of 2, where the integral is run from 0 to square root of 2 over phi. So thank you very much for watching this video, and please do subscribe to the channel. Bye.